How to configure the GNSS receiver. In this quick guide we will show you how to configure and use VX's optional multi-band GNSS receiver. The Global Navigation Satellite System receiver card in the test set serves multiple purposes. It provides accurate location used for geotagging test results. It provides accurate time of day, or TOD, for timestamping applications. Its most critical function is to provide an accurate timing reference, or 1 PPS, aligned to the standard second and traceable to the standard. The 1 pulse per second signal is used as a reference in precision timing applications. It is also used to discipline the optional built-in atomic clock, to provide more stable and reliable phase and frequency references. The addition of an atomic clock also provides holdover capabilities to bridge satellite signal outages and filters short-term phase noise out. Let us show you how to configure the GNSS reference. First, connect the antenna feed to the GNSS receiver SMA input. Although the antenna cable is expected to be well protected and grounded, it is suggested to make sure the connector is discharged of any potential static charge. Now, let's move on to the test set's user interface. From any screen or menu, tap on the System's Tools button located on the top left corner of the screen. Select Utilities, Settings, More. Then tap on GPS High Precision Clock. Select the GNSS Receiver tab and start configuring the receiver to match the test application requirements. Based on the type of antenna being used and its capabilities, select the satellite systems to be used in single or dual band modes. In this example we will use all satellite systems and all available bands, since it is connected to a multi-band antenna on the roof with excellent sky view. If the antenna needs to be powered, turn on the 5-volt antenna feed. If the roof antenna installation uses amplifiers and power injectors, then you can leave this off. The next step is to configure the location survey process. Precision timing applications are stationary and require the most accurate coordinates possible. This process is called location survey, and getting the most accurate coordinates will take some time. Precision timing GNSS receivers use a special precision timing mode, in which the accurate 3D coordinates of the receiver are known and fixed. Only time and frequency are calculated using the available satellites. This mode allows for maximum timing accuracy and stability. That is, less wander. In order to use the precision timing mode, the receiver's position must be known as exactly as possible, since errors in the fixed position will translate into time errors and wander. There are two ways to accurately set an accurate position for the timing receiver: manual and automatic survey. Using manual mode, you can manually enter known coordinates taken from accurate position records. This comes quite handy for sites that are visited often. It allows users to recall accurate values saved from previous visits, saving a significant amount of time. To do this, set the location survey field to manual. You can manually type the coordinates using the keypad to enter them in decimal degrees format, also known as DD. Or, you can simply use the load button to recall the values from a previous location survey. Using the automatic survey mode. If this is the first time at a location, and there is no accurate or trusted records from the antenna installation, you will have to enable the location survey mode. The built-in self-survey uses a statistical process to estimate the most accurate position possible. Depending on the settings and accuracy requirements, this can take some time to complete, but it is worth it. At the end, the coordinates can be saved, so you can reuse them next time. The survey is a procedure that is carried out prior to entering the precision timing mode. It calculates the receiver's most accurate position by building a weighted mean of all valid 3D positions sampled. Two major parameters are required when configuring. Observation window. It is the minimum observation time used for the position estimate. Values can range from just a few minutes for coarse position determination, up to 1 day for high accuracy requirements. Target accuracy. This is the desired standard deviation for the 3D position. It defines a limit on the spread of positions that contribute to the calculated mean. The survey process ends when both requirements are successfully met. For example, if the window is set for 1 hour, or 3,600 seconds, and accuracy is set to 1 meter, the process will lock the coordinates when the 3D deviation remains less than 1 meter for 1 hour. At that point, the coordinates are locked and the test set only focuses on timing calculations. How fast the GNSS receiver converges into the desired 3D deviation threshold also depends on the quality of the RF signals being received. Poor satellite reception or limited sky view can also slow down the process. Good antenna and antenna installation are required for precision timing applications. You may notice that better position accuracies require longer windows, so they take more time to achieve. For example, if you set a threshold window of 1 meter by 7,200 seconds, the location survey process would be considered complete when the 3D coordinates stay within less than 1 meter for a period of 2 hours. At that point the coordinates are locked and become a constant factor in the precision time calculations. That means in this case that the process will take more than 1 hour. You may be tempted to use very short windows to get a location fix quicker, but that would be in detriment of accuracy. We recommend setting the desired location accuracy, or 3D deviation threshold, to 1 meter, for the highest timing accuracy possible. With good signal, you can get to less than 20 cm 3D deviation. For field applications and quick tests, the window can be set to 1 or 2 hours. For long-term measurement applications, we recommend windows of 4 hours or more. Of course, all of that is assuming that the antenna has excellent sky view, and the receiver is getting good satellite signals. The next step is to set the antenna cable delay compensation. It requires an accurate value for the actual signal delay caused by the antenna cable feed, including any active equipment and added coaxial cords or extensions. The receiver will use this value to compensate for the delay and produce accurate 1 pps timing alignment. The time base field allows users to select the desired timescale reference, depending on the constellations being used. You can select from UTC, GPST, GLONASS, Galileo GST, or BeiDou BDT. Finally, the UTC offset, or time zone, is the difference in hours and minutes from Coordinated Universal Time, UTC, for the particular country or region you are in. This will be used to align the test set's clock to the local time of day, when the Sync TOD button is pressed. Future software versions will also include a Daylight Time Saving or DST button. Now we are ready to turn the GNSS receiver on and let it do its magic. During the survey process, you will notice that the coordinates are constantly changing, as the 3D deviation value starts converging down to the desired threshold. Although the test set is stationary, those variable coordinate errors make it look like it is moving or wandering around. As the survey process progresses, the deviation area becomes smaller and more accurate. Once the threshold window is met, the receiver changes its status to locked mode, indicating that it has stopped updating the coordinates, and that it has entered into its precision timing mode. On the status screen, you will see the final 3D deviation achieved. At this point, the GNSS 1 pps timing reference signal is considered to be in its most accurate and stable state possible, and it is ready to use. You can use the Save button to record these accurate coordinate values, so they can be used in future visits to this site, without the need of running a new lengthy survey. This is a huge time saver. Now, let's take a look at the other status sections or tabs. The Satellite View tab maps all the satellites being tracked by the GNSS receiver. They are color-coded based on their signal quality, measured as carrier-to-noise density. Since a multi-band receiver can track all the constellations at once, there may be a lot of satellites being tracked, so you can use the checkboxes to filter by specific satellite system. The Satellites tab shows a detailed list of all satellite signals being received and tracked, with their signal quality, or carrier-to-noise density values, displayed in dB/Hz. And finally, you may also see an events list that keeps a record of any significant events and alarms that may have happened since the GNSS receiver was turned on. You can now launch test applications that use precision timestamping, like PTP Precision Timing Protocol, or measurements that use GNSS 1 pps as a reference clock, like one-way delay, time error, or phase error wander. For cleaner, more accurate, 1 pps timing reference or 10 MHz frequency references, the 1 pps output should be used to discipline the optional built-in atomic clock. Make sure it shows a valid 1 pps status. Thank you for your attention and interest in VX test and measurement solutions. We hope you found this quick guide video helpful. Feel free to contact us if you have any questions or need more information. Please consider subscribing to our LinkedIn and YouTube channels to get notified about new features, quick guide videos, technology and training contents.